Hello, so welcome again to another video for AP Physics 1. This will be the review video for energy and then momentum to kind of give you that review sheet to help you out on your exam. So let me switch over to my document camera. So energy is the name of the game here, but the key with energy is energy actually starts with our understanding of work. So work equals a force times by a displacement. If that force and displacement happen to be out of line, we multiply it by the cosine of that angle. Sometimes you're going to be using this equation like this, like how much work is done on one thing versus another. But often this relates to a graph where you have force on the y, displacement on the x, and then they give you a problem like something like this, where you have a variable force, and then you have to determine the amount of work done. And the amount of work done, of course, is the area under the curve. F times D, F times D, area under the curve. Sometimes you're dealing with an object that's experiencing multiple forces, so it's being worked on in multiple ways, and you have to calculate total work, which is just the sum of all work. Nothing fancy there. Do keep track of your signs though. Some work can cancel out other work, like for example, friction is often doing negative work compared to your other things happening in the problem. So be careful of signs and what's happening there. But work, because here we're all in joules as our key unit. Work is in joules, Newton meter. So work is actually the change in energy. So here's our bridge to energy. So if you had energies changing no matter what energies they are, kinetic energy, potential energy, or just any other form of energy, those changes in energies is the work. So you can also look at work in that way. So let's separate that idea out. You do want to be aware of these two terms, that is conservative versus non-conservative forces. Conservative, those are the forces we're used to seeing. Those are mechanical energy ones. Kinetic energy, potential energy, non-conservative. You're basically just looking at friction here. In non-conservative forces, the path between matters. In conservative forces, it doesn't. All you need to worry about is initial and final conditions of your system, and you're good to go, like we do in conservation of mechanical energy. And we'll be seeing that later. A few of our basic equations: gravitational potential energy, mgh. Potential energy of a spring, 1/2 kx squared. And often related to this is Hooke's law, which is the spring force equals k times x. So you have those two equations for springs. Kinetic energy equals 1/2 mv squared. Note that both of these are squared quantities, which removes any sign that you'll find here because it's squared out, both in potential energy of a spring and kinetic energy. And then lastly, just our idea of conservation of mechanical energy can be written like this. Often for our purpose, it's KEI plus Ui equals KEF plus UF. That's often the most important form that you need. But remember, when using this, there are a couple things you need to keep in mind. Only conservative forces. So we have to be dealing with kinetic energies, potential energies, things like that. And there has to be no net external, whatever we define our system as, forces, to be able to use our conservation law. And then you have one kind of thing that sits out that you probably will never see it. And it's just this equation: power equals work over your change in time. Probably won't use it, especially this year. Then let's do it together, because they really do fall on the same vibe of things, and that's momentum. So momentum, and when you're dealing with momentum, you always just want to think about this word. Is there a collision? When things are colliding, you want to think momentum, 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 momentum of the way we solve things. So if your equations, P equals mv, note here, V is not squared. So sign matters. Sign matters a lot in these problems, and they will test you on that point, that sign matters here while it doesn't matter here. Playing with that game. And also the change in momentum equals force times time. And notice, just like above, they often like to play with this idea of change in momentum as a graph, where your force may be, again, variable, but the change in momentum is the area under the curve of your force time graph. So notice force, displacement graph, work, force, time graph, change in momentum. Think about this in follow through. This is why you follow through in a swing of a tennis racket or a bat. You're trying to increase the amount of time where you're applying a force to get the greatest change in momentum you can of that object, or the greatest velocity of that object. Then lastly, you just have to worry about this terminology. And I like to think of it as a spectrum here, where collisions are either completely inelastic, and we'll just say, we'll talk about what that is, or completely elastic. Of course, most real collisions are somewhere in between here. They don't match any of this, but these particular situations we can describe quite well. In a completely elastic case, our objects stick together during that collision. Only momentum is conserved. There we go. Energy is lost. And we're often, for completely inelastic collisions, writing our momentum conservation equation like this. Momentum of one of the objects, momentum two of the objects initially, is going to equal their momentum together, because they stick together. So you're going to end up adding their masses together here. So this is going to be mass 1 plus mass 2 times by the velocity, because they both had the same velocity after, because they stuck together. Then over here you have completely elastic collisions, where your objects bounce and where momentum and mechanical energy are conserved. These actually aren't really realistic collisions in the macroscopic world. They do happen within the atom, but besides that, they don't happen. Most things are going to lie somewhere in here where your objects don't stick together. Momentum is still conserved anywhere in here. Energy is still lost, but you're going to have a little bit fancier of equation because your objects don't stick together. If you get a problem on this, you're likely going to get one of these completely inelastic problems, though. This makes the math so much easier. Or you're going to get one of these momentum change ideas. Well, that's all we have. Energy, momentum, often going to be tested together. The famous thing is something with a ramp, objects colliding. You can do all sorts of things and all sorts of problems there that really test your knowledge of physics.